All right, ladies and gentlemen, class recording started. So today, like I said on the calendar at the beginning of class, we start getting into the applications of Newton's second law. This chapter, conceptually, is pretty straightforward. There's three things that we have to know, right? We have to know what force is, we have to know what inertia is, we have to know how force influences acceleration, and then we need to know action and reaction, which we'll talk about later on. The rest of it is all application of those things. So it's real, at its core, it's pretty simple. It's three rules that just get applied in different situations over and over and over again. And today we start working on that. So, first, gravity. We've talked about gravity a little bit earlier in this unit. What are some things that we talked about with gravity?
It acts over the longest distance.
Okay, it acts over the longest distance, but compared to the other forces, it's pretty weak, okay? Was that what you were saying, guys? Okay. What else do we know about gravity? Maybe not so much comparing it to other forces, but like what it does by itself. What does gravity do to things? Pulls them how?
Towards the source of gravity.
Towards the source of gravity, or towards each other, right? Towards together, right? What are the things that affect how much gravity exists between two objects? Mass and distance, right? And we talked about that. How does mass affect the amount of gravity, Andy? Do you remember? What kind of relationship do mass and gravity have? You want some help?
Yeah.
Okay. Direct relationship. More mass, more gravity, right? But we also talked about that the distance is a little bit weird, right? How does distance affect the amount of gravity that exists between two objects? First, what kind of relationship is it? Do you remember? It's inverse, right? But Mark, do you remember the trick about it? If not, we'll get to it in a second. So. Yes, yeah, but there's something else. So we'll get to that in a second. Okay. All right. So let's go here, right? So gravity, attractive force that exists between any two objects. We probably should put any two objects that have mass, although you can't really have an object if you don't have mass. So kind of a chicken or egg sort of thing. And then, so first, attractive force, right? It pulls things together. Okay. It depends on mass, which has a direct relationship, but it also depends on, X. That means as the mass goes up, gravity goes up, and as mass goes down, the gravity goes down, right? But it also depends on distance. It's an inverse relationship. But we talked about that it's actually, we should clarify this, right? It's actually an inverse square relationship, right? Our first example that we come up with, actually not our first example, but an inverse square relationship where, right, as the distance goes down, gravity goes up, but by the square of the distance, okay? Meaning that if you go from 1 meter to 1/2 meter, there will be more gravity that exists between you and the object. But there won't be twice as much gravity. There will be 4 times as much gravity, because 2 squared, right? Or if you go from 1 meter to 1/3 of a meter, right? It won't be 3 times as much gravity. It'll be 9 times as much gravity because it's 3 squared, right? Same thing works the other way, right? As distance goes up, gravity goes down. If you go from 1 meter to 2 meters, right? There isn't half as much gravity. There's 1/4 as much gravity. If you go from 1 meter to 3 meters, it's not 1/3 as much gravity, it's 1/9 as much gravity, right? So the inverse square relationship, which shows up a lot out there in nature. Gravity is an example of it, electrostatics and other things too. Shows up a lot, okay? All right, good there. Okay, so let's talk about our gravity, or the one that we deal with the most, and that's gravity on Earth. Right? Earth's gravity pulls objects towards its center, right? We think about it as pulling objects down, right? That's generally how we talk about it, right? But really it's pulling things towards the center. down for us is a different direction than down for people in Australia or down for people in China, right? If they're on the other side of the earth. But it's still pulling things towards the center, okay? That being said, gravity can cause what kind of motion changes? What can gravity do to an object? Hold up. So, if I take this and I drop it, what's gravity going to do to it? It's going to pull it down. What's going to happen to it as it's pulling down? It's going to speed up, right? So that's one type of acceleration, okay? What about I throw it upward? What's going to happen? It's going to slow it down first, then speed it up, right? Okay? So we've got two of the three forms of acceleration, right? Can it cause something to change direction? Yeah. Give me an example.
Like with the ball, you threw it up and it changed direction.
Okay, I'll give you that. That was exactly what I was thinking of. But yeah, when it goes up, it comes down. That's a change in direction. Nick, what else are you going to think? What were you
There's like a meteor or something.
a meteor, or let's go with something like, if we do this, right? Well, not, something a little less extravagant as a wormhole, right? What does this? The moon, right? Okay, it causes the moon to go around in a circle around Earth, right? So let's hold on. Let's go to the moon first before we go to wormholes, all right? All right. So gravity, because it's a force, causes acceleration, and it can cause any one of the three types of acceleration, or sometimes more than one at the same time. Okay? Now, Eris, getting back a little bit to what we talked about, what you kind of brought up at the beginning. We think of gravity as a really strong force. Think of what we have to do to get a rocket to overcome gravity. Not leave gravity, but overcome the force of gravity, right? If we want to get something, to orbit the Earth or get it out of the atmosphere, which in the grand scheme of things is very small, think about the kind of force that we have to apply. So we think about gravity as being very strong, right? But, Eris, you brought up at the beginning, right? When you compare gravity to other forces, it's actually pretty weak. It's not very strong. But two factors, right? Earth has a very large mass, and we are really, really close to it, right? So those two factors combine to make the effect of Earth's gravity relatively strong for us, right? But think about the fact that, our gravity affects the moon, right? But the sun's gravity is strong enough to affect, like, Neptune, right? I don't want to say Pluto and start that debate, all right, about whether Pluto's a planet or not, or we won't go there, but, right? That's good.
You say we're so close. You mean we're so close to the center of the Earth?
Technically, yes, even though we think about, the center of the Earth is a really long way away, right? It's actually like 3,500 miles about, okay, about 6,500 kilometers. But big picture-wise, right, we are really close to the center because we're on the surface, right? I mean, we're much closer to the center of the Earth than we are to like the center of the sun, right?
I just get kind of confused. Like I thought you might meant like our mass is close to the Earth's mass.
Technically, that's true. No, I'm sorry, not as a comparison, as a distance, right? Remember, two factors, mass and distance. Earth has a large mass, and we are relatively close to it, not in how big our mass is, but in our distance to the center. Yeah, sorry. Is that good? Yeah. All right. Good there? But keep in mind, Earth's gravity is not the only gravitational force that we experience. You experience a gravitational attraction to any other mass. You are gravitationally attracted to your pencil because it has mass and you have mass. There is a gravitational force between you. Right? There's a gravitational attraction between you and the person sitting next to you. Right? Because you have mass and they have mass. So there's a gravitational attraction there. But Earth's mass is so much bigger than all those other masses, its gravity sort of trumps all that other stuff, right? Technically, as I drop this ball, right, does it fall straight down? Not really, right? Because, well, there's me on this side of it, right? But there's all of you on that side of it. So technically, it should kind of, you know, fall diagonally towards you guys as it's falling downward. But your gravitational pull is so insignificant to the Earth's, we really don't experience that. Okay. Good there. All right. Earth's gravity is not something we can get rid of. It affects everything that we do, regardless of motion, mass, etc., etc., etc. Please, 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 please. I don't know how many that was, maybe 12, okay? But you'll understand why. When you leave this class, all right, and you talk about like astronauts or something, please don't tell anybody that astronauts float because there's no gravity, okay? Please don't tell anybody that. It's not true. Okay? There's gravity there. And as a matter of fact, astronauts in orbit feel about as much gravity as you feel on Earth. A little less because they're farther away, but in the grand scheme of things, not very much different, right? It's other things that are going on. It's not because Earth's gravity stops, right? Okay? But please, 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 please don't do that. Okay? Makes me look bad. All right, good there. But there is something that we experience. Earth's gravity does affect all objects, but even though they might have different masses, what we find out is that Earth's gravity affects them the same, right? Ready? So, if Earth's gravity affects them the same, what should we see about these two objects?
Fall at the same speed.
They should fall at the same speed. Did they fall at the same speed? No. Okay? So, am I lying? No, not really, right? When we look at the acceleration of an object, we have to look not only at the mass of that object, and not just at one force acting on them, but all of the forces, right? Gravity does affect both of these objects, and we'll see here in a second it affects both of them the same. But this one is more susceptible to air resistance, which gets us into the next part of our discussion, right? This one, because it's round and because it's fairly solid, not really affected by air resistance all that much, okay? But if we change this one and minimize the effect of air resistance, okay? For dramatic effect. If we minimize the effect of air resistance, right? Gravity pulls them down side by side. They keep going at the same rate. They keep accelerating at the same rate, so they stay with each other, and they end up hitting the ground at the same time. Good there. So why? Why does that happen? Are they feeling the same force? There's. They have different masses, right? Remember, gravity, the gravity that exists between two objects depends on the mass of those objects. Gravity exists between this ball and the Earth, so the Earth has a certain mass and this ball has a certain mass, right? But gravity's acting between the Earth and this piece of paper. Do the paper and the ball have the same mass? They don't, right? So they have different forces acting on them, right? But, like we just discussed, what else is different about them? The acceleration of an object is affected by two things. What two factors affect the acceleration of an object? The mass and the force, right? So, Suzanne, we've already established which one of these feels a greater force. The ball, because it has more mass, right? But, because it has more mass, it also has more what? Gravity is the force that's acting on it, right? So it has more force, but it also has more what? Inertia, right? Meaning, even though it feels more force, right, it's harder to get it to start moving. The end result of that being, right, that more force, yes, but more inertia means it's harder to get it to go, and they both end up experiencing the same acceleration. Okay? So, let's review. All right. Exactly there. Let's go here. Okay. So what? Let's not go there either. All right. Let's go here. Okay. So we established earlier that mass is a measure of how much inertia something has, right? It's how much stuff is there, but it's also how much inertia that object has, right? Mass is not going to change regardless of where we go. This ball, wherever it ended up, okay, this ball has the same mass here on Earth that it does if we took it to the moon or if we went to the sun, right? It might not be together anymore, but it would still have the same mass, okay? Or if we took it anywhere in the universe. But if we took this ball and dropped it here, and we took it to the moon and dropped it there, we would find out that on the moon it actually falls slower than it does here on Earth. I'll show you a video of that in just a second. Because it's just as easy or hard to get something to move on Earth as it is on the moon. Okay? Because the weight of an object will change. By definition, the weight is the force of gravity that is acting on an object. You weigh less on the moon than you do here on Earth. Is there anything fundamentally different about you on the moon than there is on the Earth? No. You have the same mass on the moon, but the force of gravity on the moon is less because the mass of the moon is less, right? The amount of gravity acting on an object depends on the mass of the object and the acceleration caused by gravity at that location. The acceleration caused by gravity at that location is affected by the mass of that object. So shorthand, what we do, we can calculate the weight of an object by taking its mass and multiplying it by lowercase g. And hopefully you remember from last unit that that lowercase g represents the acceleration that is caused by gravity at that location, which, whereas on Earth is approximately 9.81 meters per second squared. So we can calculate the weight of an object by taking its mass and multiplying it by 9.81. Now, you'll find out that if you do that here on Earth, you won't get your weight, or what you get when you step on the scale, because this will give you your weight in newtons, right? Weight is a force. It's how strongly does gravity pull on you. How many newtons does gravity apply to you to cause that acceleration? So don't go home and pop in your mass and then multiply it by 10 and say, wait, that's not what I weigh, right? That's what you weigh in newtons, right? It's a force, okay? All right, good there. Okay, to illustrate that point, and maybe to bore you like a little bit, just a little bit, let's watch this sweet video. All right, so I'm going to do this, and I'm going to zoom in, because if I fit to screen, the orientation gets all messed up, so I'm just going to zoom in here. All right, so this video is a whopping 2 minutes and 16 seconds long, all right? So see if you can, it would be 2:07. Anyway, it's a little more than 2 minutes, but anyway, okay? See See if you can hold your attention for 2 minutes. And here we go. Sorry, it's 2:05. All right. So let's discuss the video. First part of the video, dealing with the feather and the penny, right? If we can get rid of the air resistance and focus only on the gravity, making gravity the only force that is acting on an object or two objects, we will see that gravity causes the same acceleration for those two objects, right? Suzanne, we kind of talked about that, right? Gravity is affecting the penny more in that example than it is the feather, or at least applying a greater force. But because the penny has a greater mass, right, it slows it down, and the effect cancels out, and gravity affects all objects the same way, or accelerates all objects the same way. But at the end, you saw that as another example, the feather and the hammer. It works on the moon because what's missing on the moon? The air resistance, right? The atmosphere providing that second force, okay? But the one thing I tried to illustrate with my example, I have a book which is heavier than a feather, but maybe lighter than a hammer, all right? And I dropped it at approximately the same time that astronaut David Scott dropped his objects from approximately the same height, right? We were both holding them shoulder height. He might be a little taller than me, but whatever. But what did you notice about when the book hit the ground versus when the hammer and the feather hit the ground? Did you notice? Book made a noise, true. When? A little before the hammer and the feather hit the ground in the video, right? Do we want to watch again? You don't have to watch. We don't have to listen to the commentary. So, hammer, feather. So, all right, we take a rock or a book or a hammer or something heavy, okay? And we drop it on the earth and we drop it on the moon. And we find out that the rock or the hammer or the book falls faster on the earth than it does on the moon. Why? Say again? Gravity affects it more. Why? What has more mass? No. The rock has the same mass here as it does on the moon, but
The moon has less mass.
the moon has less mass than the Earth, right? Remember, gravity is a two-way street. You've got to have two objects in order to have gravity, right? They have to pull on each other. The rock is the same whether it's here or on the moon, right? But the moon has less mass than the Earth, so the rock experiences a greater force here on the Earth than it does here on the moon. Which is different, right, than this picture on the left, right? In this picture on the left, the rock and the feather, the rock is falling faster than the feather. But as we discussed, does that mean that the rock is experiencing a greater acceleration than the feather? In this picture, technically yes, right? But that's not gravity's fault, right? It's because the feather is more, Earth has more mass than the moon, which means the force of gravity is stronger. More gravity, more force, more acceleration, and that means it's speeding up. All right? But, right, on the moon, the rock and the feather, or the hammer and the feather, as we saw in the video, right, fall with the same acceleration. Why? Because, right, the rock has a larger mass, so it does feel a larger force of gravity. Not as large as it feels here on Earth, but larger than the feather. But the rock has a larger mass, which means it has more inertia. More force would make it go faster, more inertia would make it go slower. The end result being, gravity makes all objects accelerate the same rate. Because, as it says in Roman numeral 4, letter A, right, the acceleration of an object depends on two things. What are the two things that affect the acceleration of an object, regardless of where or what's causing it?
Mass and force.
Let's go with not just force, but
Net force.
net force, right? So mass and net force both affect the acceleration of an object, right? So in the case of the picture on the right of your outline, right, the rock does feel a greater net force, but because it has a greater mass, those two factors cancel each other out, and we end up with the same acceleration. All right, good there? Okay. Let's call it a day. If you look on the calendar, there's a couple pages from the book dealing with these ideas and a couple questions. The sheet that's attached to your outline will deal with that in class a little bit more tomorrow. Yesterday. Yep. Yeah, one per group. One per group, yeah, for the scooter lab.